We have a quarter circle JKL with center at K, and inside that quarter circle there is a smaller circle touching the left side JK. A vertical segment UV is drawn from the arc, straight down to the base KL, and this segment is tangent to the smaller circle. We are also told that the length of UV is 4 units, and our goal is to find the exact area of the shaded region between the large quarter circle and the small circle. Let's begin by introducing some variables. Let the radius of the large quarter circle be t, and let the radius of the smaller circle be s. Now, the shaded area is simply the area of the large quarter circle minus the area of the small circle. The area of a full circle is pi times radius squared, so the area of the large quarter circle is pi times t squared divided by 4. The area of the small circle is pi times s squared. Therefore, the shaded area equals pi times t squared divided by 4 minus pi times s squared. Notice that both terms contain pi, so we can factor it out. That gives us area equals pi multiplied by the quantity t squared divided by 4, minus s squared. So from this point forward, all we really need to determine is the value of t squared, divided by 4 minus s squared. Now let's use the geometry of the figure. The small circle is tangent to the left side JK, and also tangent to the vertical line UV. Since those two lines are parallel and this circle touches both of them, the distance between the two lines must equal the diameter of the small circle. Since the radius is s, the diameter is 2s. Therefore, the distance kv equals 2s. Now connect point K to point U. Since U lies on the arc of the quarter circle and K is the center, segment KU is a radius of the large circle. Therefore, KU equals T. Next, focus on triangle KUV. Because UV is vertical and KV is horizontal, triangle KUV is a right triangle. Its horizontal side KV equals 2s. Its vertical side UV equals 4. And its hypotenuse, KU, equals T. Whenever we have a right triangle, the Pythagorean Theorem tells us that the square of the hypotenuse equals the sum of the squares of the other two sides. So we get the quantity 2s whole squared plus 4 squared equals t squared. Let's simplify that carefully. The quantity 2s whole squared becomes 4s squared. 4 squared becomes 16. Therefore, we have 4s squared plus 16 equals t squared. Now divide every term in the equation by 4. 4s squared divided by 4 becomes s squared. 16 divided by 4 becomes 4. And t squared divided by 4 becomes t squared divided by 4. So we obtain s squared plus 4 equals t squared divided by 4. Now subtract s squared from both sides. On the left side, s squared cancels out, leaving 4. On the right side, we get t squared divided by 4 minus s squared. Therefore, 4 equals t squared divided by 4 minus s squared. Pay attention to this result, because this is exactly the expression that appeared inside our area formula earlier. We found that area equals pi multiplied by the quantity t squared, divided by 4 minus s squared. But we have just proven that t squared divided by 4 minus s squared equals 4. Substituting that value into the area formula gives area equals pi multiplied by 4. Therefore, the shaded area equals 4 pi square units. And that's the beautiful shortcut in this problem. We never had to calculate the large radius. We never had to calculate the small radius. and we never had to solve for any unknown lengths. The tangent segment of length 4 alone completely determines the shaded area. If you enjoyed seeing how the Pythagorean theorem unlocks the entire problem with almost no computation, be sure to like the video, subscribe for more elegant geometry tricks, and let me know in the comments whether you spotted the shortcut before we reach the final substitution. The exact area of the shaded region is 4 pi square units.